On a lonely strip of tarmac, under the pale glow of hangar lights, the sleek black shape of the SR-71 Blackbird sits like a predator waiting to hunt. Its surfaces gleam with secret heat, and somewhere far above, a spacecraft bearing human dreams arcs across the void, guided by nothing more than metal, wiring, and the blueprint of mankind's ambition. Tonight, I invite you to cross the threshold between supersonic shadows and lunar dreams. We will journey through the tale of the Blackbird's daring speed, the Apollo Command Module's blueprint that carried us to the moon, and the link that binds human curiosity across air and space. The Blackbird, a phantom of speed, the SR-71 Blackbird was born in secrecy, conceived by Lockheed Skunk Works under the hands of design legend Clarence Kelly Johnson. It was not a fighter, not a bomber. It was the ultimate reconnaissance machine designed to fly at Mach 3 at extreme altitude, to spy and vanish. To look at the SR-71 is to see contradictions. Inky black paint yet blazing hot at speed, built to last yet so delicate it could leak fuel on the ground. Its skin heated to hundreds of degrees from air friction. Its shape molded to survive shock waves. Pilots flew it like a bullet carved through the sky, trusting that their machine outrun missiles, rather than dodging them. In its guts, the Blackbird carried cameras, sensors, radar, and spy instruments. It listened to signals, looked across borders, and returned secrets to Earth. It was a ghost in the sky. No SR-71 was ever shot down by enemy fire. Its defense was its speed and altitude. This is the aircraft that embodies the edge of what is possible in the atmosphere. Yet beyond the thin blue line, humans dared to go further, to the moon. And to do that, they needed a vessel that would survive the vacuum, radiation, re-entry heat, and still bring them home safely. That vessel was the Apollo Command Service Module. The Apollo CSM, blueprint of a dream, the Apollo spacecraft's heart was the CSM, the Command Service Module. It comprised two parts: the Command Module, the cone-shaped capsule that housed the crew and would make the daring plunge back through Earth's atmosphere, and the Service Module, the cylindrical engine room that supplied propulsion, power, and life support. From the earliest days, engineers worked to turn bold sketches into precise blueprints. The command module's profile, its heat shield geometry, its thicknesses, windows, hatch, structural supports, wiring, all had to be exact. The service module's tanks, plumbing, radiators, engine nozzle, and structural ribs all had to find a delicate balance between mass, strength, and reliability. The blueprint of the command module is iconic. It is a truncated cone, about 12.8 feet across the base, about 11 feet tall. Its outer shell was a stainless steel honeycomb sandwich. Inside was an aluminum pressure vessel, insulating layers, wiring bundles, and life support systems. It had 5 windows, 2 side windows, 2 triangular rendezvous windows, and a small hatch window overhead. Inside the cabin were 3 couches, control panels, guidance systems, environmental systems, and storage for food, water, and waste. The service module, unpressurized, held propellant tanks for the main engine, oxidizer, fuel cells for power, radiators to dump waste heat, reaction control thrusters, tubes, piping, and a high-gain antenna for communication. The main engine was the HA-137, burning hypergolic propellants capable of being restarted multiple times. 3 tension ties and 6 compression pads held the CM and SM together. The modules transferred power, fluids, and consumables through an umbilical. At re-entry, the umbilical was severed and the service module jettisoned to burn up in the atmosphere. Engineers drew and redrew. They tested thermal models, pressure tanks, shock loads, and vibrations. They risked lives in tests. The blueprint was not a decoration. It was a lifeline to safe passage. Block I of the CSM was for early testing. Block SICM became the lunar version, with docking capability and improved systems. The hatch design changed after the tragic Apollo 1 fire. The Block CU hatch was a quick, release outward opening design for better safety. The arrangement of antennas, radiators, tanks, and structural elements was refined in each version. At the heart of it all, the blueprint of the Apollo Command Module is a testament to human precision, fear, and faith. Every millimeter mattered, every bolt, every layer of shielding, every connector might decide life or death. The bridge between air and space, you may wonder, what connection is there between the SR-71 Blackbird and the Apollo CSM blueprint? At first glance, none. One is a plane, one is a spacecraft. But at a deeper level, they both represent the apex of human engineering, pushing materials, heat, speed, and daring to extremes. When the SR-71 races through the stratosphere, its skin glows, its structure flexes. Pilots trust that their aircraft won't break apart, that the skin will expand, that fuel won't boil away. That trust comes from blueprints, wind tunnel tests, materials research, and daring assumptions proven over years. Similarly, when astronauts sit in the command module nearing reentry, they trust that heat shields withstand plasma, that structural supports hold, and that the blueprint they flew by was rigorously validated. Errors are fatal. In some Apollo missions, the service module carried a scientific instrument module, a camera that mapped the moon, derived in part from imaging technologies originally developed for reconnaissance aircraft. The linkage is not direct to the SR-71, but the spirit is common: reconnaissance observation, pushing the frontier. In museums today, you might see an SR-71 and an Apollo command module on adjacent display. In one you see an airplane built to peer at nations, in the other a spacecraft built to carry nations' dreams. The same human impulses: see, understand, push outward. A mission in blueprints and shadows. Let us imagine a narrative. A group of engineers in the 1960s sit around drafting tables. In one room, the Blackbird team sketches the chines and air intakes, debates stealth thermal expansion, and skin joints. In another, NASA engineers draft the command module cross-section, define hatch tolerances, thicknesses of honeycomb, heat flux, and radiators. They work late nights under fluorescent light. They refer to test data, wind tunnels, heat ablation tests, and pressure vessel stress diagrams. Each line drawn is deliberate. Each revision means new stress analyses, mock-ups, and test rigs. A structural analyst leans over the command module blueprint and whispers, "If we reduce this flange thickness by 2 mils, we save weight. But can it survive the triple G load on reentry?" The room falls silent. They consult simulation and test results. They revise. At the same time, a SR-71 inlet designer argues about shock wave reflections and boundary layer bleed slots. The intake must compress supersonic air smoothly. Any mistake might stall the engine at 3 times the speed of sound. That engineer consults diagram after diagram, tests scale models and wind tunnels. Though their goals differ, one to spy, one to explore, their challenges echo material limits, heat, stress, fluid dynamics, and above all risk. They both must trust the blueprint. They both must push the margin where failure is not a lesson, but disaster. Flight, launch, and return. Imagine the SR-71 roaring down a runway, afterburner spooling, then ascending toward Mach 3. It flees threats, executes recon, then returns to base, carrying data. Its mission is high speed, high altitude, returning with secrets. Now imagine Apollo 11 Saturn V launches, the CSM climbing through turbulence, staging, and trans-lunar injection. The command module and service module separate from the upper stage, then later dock with the lunar module. The astronauts spend days in deep space, burn engines, make course corrections, then return home. The service module is discarded, and the command module plunges through the atmosphere, deploys parachutes, and lands in the ocean, bringing men home. The SR-71 never leaves Earth. The Apollo CSM never returns to Earth intact, except for the command portion. Yet both journeys rest on faith in engineering. The blueprint of the command module, the calculations behind the service module, determined exactly when to burn, exactly how to approach reentry, and exactly how to manage heat. One miscalculation, one weak weld, one misrouted wire, and catastrophe. When Neil Armstrong's boots touched lunar dust, the command module Columbia waited for him. When Eugene Cernan stepped back inside on Apollo 17, the blueprint-born capsule would carry them home. The SR-71 missions gathered intelligence that shaped Cold War decisions. The Apollo missions reshaped humanity's horizon. Both changed our view of Earth. Both required us to trust fragile shells of metal over unimaginable distances. To the moon and beyond. So tonight, when you look at pictures of the SR-71's sleek form, or the Apollo command module's blueprint diagrams, remember this: they are not just machines, but monuments of human faith and design. In shadows above, we raced speed. Into space beyond, we launched dreams. If you've enjoyed this journey through Blackbirds and lunar blueprints, hit like, share with your friends, And don't forget to subscribe. Your support fuels more stories of engineering, exploration, and wonder. Press that bell icon so you don't miss our next adventure. Maybe into Mars, the edge of the solar system, or deeper in human ingenuity. Until next time, keep looking upward and stay curious.